A lot has changed since the last time I stood at this podium. As an example, after the next break, and yes, I'll be done in time for you to participate in that, after the next break there will be a panel, and the panel is to be on exascale computing. Specifically, the title of the panel originally proposed as much as a year ago was, and I quote, DARPA UHPC. For those of you in the know, there should be a slight chuckle. I received a message from an individual. I won't name this person. Notice how carefully I was gender unspecific. I received a message, and it said, given the changes in our program goals, we would appreciate you making a slight modification to the title of this panel. Specifically, we would like you to remove the term DARPA. We would like you to remove the term UHPC. Everything else is fine. That's the bad news. There's also a significant amount of good news. We'll discuss more of these at the panel. I decided that I would like to take this opportunity to do something I've never done before. There's not a single slide in this deck that I have ever given before. The good news is it's completely new. The bad news is, well, I haven't ever practiced giving this talk, so I will struggle through it. My intent is to discuss the meta roadmap, or the path to building a roadmap for exascale computing. And even at this early time, by looking at the substantive issues that relate to this, we can draw some, I think, seminal conclusions and ask some really critical questions at this time. One thing I'll tell you right up front is the clock is already ticking. Perhaps it's already too late. To talk about a path to exascale requires that we consider a number of factors. The challenges, what about those we don't yet know? What do we anticipate without complete understanding to be the major components and methods? What are the capabilities that we require that nonetheless do not neatly get packaged within a single component or a single layer and ultimately are cross-cutting? Is it premature to consider the actual timeline to achieving exascale? And if we don't know things, what do we have to find out? What are those research objectives? What are the tasks to fulfill those? Clearly, building a machine merely 100 times as powerful as the largest machine that we're approaching today. How do you actually develop and implement that thing? And then I'd like to conclude by reviewing that briefly and asking a really fundamental question. Are our assumptions correct? And if this were an objective talk, I would let you conclude that, but I'm going to give you my answers. So I think with Euclid, isn't that sophisticated the way I bring up Euclid? I believe it was Euclid who had, and now I better get this right, 5 fundamental laws of geometry. Somebody tell me it's 6. Is it 6? It's 5. Thank you. Okay. And I tried to come up with 5 fundamental goals and requirements for exaflops. So first was easy. We want to get exaflops as sustained performance. The second, we seem to be in this lemming race, and I'm part of the problem, to do so before the end of this decade. The third is, unlike when we got to petaflops, oops, did I say that? We want this to actually be of value for real-world applications. We want the system to be practical and useful and reproducible and marketable. Now that's my 5. And I'd be happy if someone would add one, remove one, or do some synergy, but I think it pretty much captures what we're talking about. Now my comments over the next 20 minutes or so are derived from a body of experience that is constantly increasing and comes from a number of programs, projects, studies, and workshops by multiple agencies. And I want to thank those who both drove those programs forward and all my colleagues with whom I have collaborated on these. There have been some additional programs that I have not been part of. For example, I'll mention it later, the Department of Energy's co-design program out of Office of Science. And I haven't had the privilege to participate in that, which means I didn't get the money. But they're also an important component. Now, not all programs are created equal. For an example, the DARPA UHPC program, a 4-phase program that will end in 7 years, except it's coming to an end this summer. This was supposed to be the final world. Although never officially an Exascale project, it nonetheless was committed and dedicated to the development of technologies which themselves would have permitted exascale computing. The program is coming to an end. A new program, by coincidence, is started. The RFP is out. The program is called Perfect. A number of you may have already seen this RFP. It's to focus now on embedded computing with almost exactly the same requirements as the UHPC program had. I'm not smart enough to understand this. So we all get to write the proposals again, but it can't fall into the category of exascale computing, although the technology to be developed under such a program would in fact help facilitate, drive forward many of the necessary requirements. In fact, although it didn't show up in the RFP, the embedded computing domain does, in many cases, require real-time management. This has been outside the scope of exascale computing objectives in the past, but in fact, needing the introspection of runtime control, which we'll discuss a little bit later. Real-time operation is actually an important, or will become an important part of the fundamental operating environment of these machines themselves, which is a major change in the way we do computing. Now, let's be clear. There are multiple modalities of HPC. To talk about the single supercomputer is like talking about the single Republican Party, right? And I don't know which is the conservative wing and which is the ultra-conservative wing of the Republican Party here. So a simple division would say capacity or throughput computing, where essentially job parallelism in the extreme is used to bring up the total throughput or the operations per second that are performed. Versus capability computing, where in a ideal case, as you add more resources to a fixed size problem, the execution or response time actually shrinks. I have coined the term cooperative computing to consider the alternative, or let me rephrase that, the intermediate ground where you do work on a single problem, but you allow that problem to grow to fill its container. But right now, let's focus on these two extremes. We are not talking about capacity computing or throughput computing when we talk about exascale. I mean, we have something like that. It's called the internet. We don't need to reinvent that. Cloud computing is emerging, and one of its attributes is the potential, the promise for doing cost-effective throughput computing. It's not as easy as that, but there are multiple ways of achieving that. Right now, we're talking about the needs of science, technology, engineering, and mathematics, STEM-like problems for the challenges that really face moving the edge of the envelope of civilization forward, and yes, also national security. Now, my last preparatory comment, which gets us halfway through the talk, by the way, is that the assumptions upon which my position is based is considered controversial by much of the community. Many of the really good people in the community fundamentally disagree with me. I want to be clear about this. It is my conclusion that a revolutionary strategy, and by that I mean a strategy that differs markedly from the last 20 plus years, is required in order to meet the goals of the end of this decade. The alternative approach, that of continuing the path that we have done over the last 20 years very successfully, involves incremental changes or incremental advances using as a baseline conventional MPP architectures and processors with some changes, adding extensions to existing programming interfaces. The phrase is MPI plus X, or if you want to get really radical, MPI plus X, here it comes, plus Y. It's almost an unstated assumption that there'll be a Unix-like or Unix-based operating system, that the legacy codes will run fresh out of the box, and that the overall approach to making the necessary advances is bridging the gaps. This is a subtle, attractive, and insidious mindset. You see, the idea of going out and identifying the gaps between where we are and where we need to be in Exascale, and then filling them, assumes that everything we've been doing to date, so far, is already good for Exascale. And as much as I would like to believe that were true, it's not, in my view. We have faced this problem before when we went to terascale and when we went to petascale. And in those cases, the methods that provided us with those increased performance gains of triad decades did succeed, because the fundamental advances were at the technology level that brought us the performance gains. That's no longer that's no longer the case, as we well know, as we're now part of the multi-core era. This is almost a mantra of the Exascale community. You probably have your own list, but this is pretty generally accepted. The order is what I think a priority, and it's my order. Others would put it quite understandably in a different order. I think the number one problem is parallelism. We need on the order of 10 billion way concurrency. Right now we're approaching 1 million cores in a system. With the GPUs, you may feel we've already crossed that, depending on how you count cores. We need to go another 10 to the 4th in terms of parallelism. And then, of course, there's the low-level ILP, which I'm sweeping under the rug. The second requirement is efficiency. We throw away 9/10 of our machines, at least by certain measures, and we need that back. We need that back for time, we need that back for cost, and we need that back for power and energy. Reliability is crucial. The checkpoint restart methods that we've used so successfully, reasonably successfully over the last 2 decades, become non-viable when you do the statistics, and you see that the time to checkpoint is larger than the mean time to interrupt, with the failure of the number of devices that will be involved. Some would consider the biggest problem to be power and energy, and those two really are different things, although clearly closely related. The reason why I don't put it at the top of the list is because, well, in the end, we could build a machine at ridiculous amounts of power. The comfort zone, another subjective cost, is something in the order of 20 to 25 megawatts. Estimates of the amount of power that would be used without dramatic changes in the way we do the business goes up to on the order of 400 megawatts for an exascale LINPACK. We anticipate we'll be able to bring that down, but it will require dynamic techniques. Another requirement is generality and portability across machines of different types, of different scales, and all important, of different generations. Generality is a bit controversial when devices like Anton manage to achieve, for a narrow scope of problems, just a tremendous gain in advance, as do some problems with conventional GPUs of today. And yet, generality is likely to prove the dominant mode of both marketable and usable systems because the diversity of workloads greatly exceeds the opportunities for specialized hardware. The others are also obvious. Programmability and usability, those are major challenges. And yes, let us not forget cost. Now, if this were a talk about teraflops 20 plus years ago, or a talk about petaflops, and yes, I've given many 10 years ago, then we might not have this slide, but it isn't. We're on a different part of the S-curve of the technology. We don't even know the paradigm by which we want the computation to be performed. I have given a talk on this subject at this conference before. I won't dwell on the point. But with the challenges and the technologies allowing us or forcing us to do things differently, we need an underlying framework, a concept, a methodology, ultimately embodied in the execution model to be able to do this. We don't know where the billion-plus way parallelism is going to come from. I anticipate it's buried and it's intrinsic in the metadata of the large, complex, and often time-varying data structures as well as irregular that we will be dealing with. But other than streaming or throughput computing, we have not seen in general where that parallelism is. And even if we had it, debugging, if there's one thing that scares me, it's the debugging. And while I write perfect programs, I can't expect that of everyone. Okay, not only do I not write perfect programs, I almost don't write programs. And I don't think working in MATLAB counts, do you? How many printfs can you execute? We have to bring the power envelope in line, and although there are good ideas, we're not there yet. And, heaven forbid, we need a new programming interface, a new parallel programming language. And nobody wants to talk about a new language. What are the jokes? It'll be called Fortran, it'll be called MPI. The fact is that with a different paradigm, the need for extremes in orders of magnitude of parallelism, we really need to talk to our machines in a very different way. And finally, we need to ask the question, should there be a processor core architecture that is good for something other than laptops and maybe small nodes for enterprise servers? Indeed, I think it's going to be clear that yes, we will need a processor that's different than the processor for enterprise servers today, but no, those processors won't be different from what enterprise servers can effectively use in the future. Okay, here's the good news. We can all put this list together. Even if you think you're going to use something very, very radical, as long as it's not quantum computers, then there's a problem with quantum computers. So years ago, maybe one or two of you know this, many years ago I worked with multiple federal agencies to explore the possibilities of exploiting single flux quantum. This is superconducting supercomputing gates. A very interesting project. Needless to say, it didn't get built. Why? Well, it was 4 kelvins. They needed 4 kelvins. This is liquid helium temperatures. Everyone said to me, no one will ever use something as cold as 4 kelvins to compute. So, unless, of course, you write a proposal to do quantum computing, which makes absolutely no sense whatsoever, and it's at 20 millikelvins, and nobody has a problem with that. So I've come to a conclusion that the more extreme your requirements, the more ridiculous your proposition has to be in order to sell it. You know, how would I write the quantum computer proposal? It would go something like this. If I could build this thing, which is impossible, it would revolutionize computing. And they get the revolution part right. And they actually, and no pun intended, think the 20 millikelvins is cool. And they forget the impossible part. Operating system, runtime system, programming models, and the appropriate compilers. Changes to the system architectures in some sense blurred off from a certain distance will look pretty much the same. Focus down with a microscope, and there will be significant changes. The new relationship between what becomes processor cores and the memory banks. The relationship between processors, cores, and guess what? Other processor cores. The network actually becomes a computer. The memory assimilates the network. Yes? Resistance is futile. Sorry. And one is always supposed to put down mass storage in I/O. And it's so important to me that I won't mention it again. Right, now, in spite of the fact that we understand the layers, many of the components, we don't necessarily understand the functionality. We certainly don't understand their interrelationships. There are a number of new cross-cutting capabilities that are supported by all these layers, including the abstraction of the execution model. The need for a dynamic framework, let's call that introspection or self-aware, to borrow from other DoD and DOE programs. The need to find and exploit parallelism that we haven't touched before. You know, to date it's been very coarse-grained at the process level and a few fine-grained ILP instructions down at the reservation stations and so forth. We now have to focus on the reality of asynchrony management to avoid blocking, which can lose our time and our power. And all these different layers have to provide the power control and have to contribute to the reliability, the resilience of these systems. And this requires co-design. Not simply developing a runtime system that then connects up with, let's say, a Unix or a Linux. Yes, we've done that. But rather redefining the underlying foundations and making sure that they interact as much by the roles and responsibilities of the runtime system as the runtime system does with the operating system, and take any slice through that system, and you still have that pairing of relationships that have to be redefined. So, I don't think I can get through a talk without saying starvation, latency, overhead, and waiting for contention. Okay, I've said it, I got it out of my system. These are the killer factors that contribute to performance degradation across the last 60 years of computer definition, and for almost every moment in every paradigm in supercomputing, the approaches assumed at that time with that technology were driven by these requirements, and this must happen again, and the answer is different from what it is in POX MPI in the last 20 years. We need to understand that execution model, and then we need to manifest that execution model principally in the interrelationship of the operating system and the runtime system. They're not the same thing. In a way, the runtime system is dedicated to the user requirements and to a first-order reduction of the user application execution time And it's ephemeral. It's instantiated when the user application is instantiated, and it dies when that application is complete. Alternative, the operating system is just the opposite. It is persistent. The operating system fights for the system. The runtime system fights for the user, is a phrase I should have copyrighted some time ago. The operating system has to maintain the complete job stream optimization. It's a different objective function, and it is responsible for things like reliability and power management, though it must share that process with other layers of the system. We must also engage in the research on the new memory model. You know, the memory model is so archaic, and it is still our principal challenge. In fact, we confuse things with, like, memory consistency. We think, well, we have a parallel programming or parallel computing model, and then we have the memory consistency problem. No, what we've done is we've inadequately, loosely defined the parallelism model, and as a result, we have an error. The error is a consistency problem. Right. I'd like to talk for a moment, one slide, on execution models. This is not so much about my favorite model, which is in parentheses, but rather is a recognition that through the community there is an undercurrent of realization that there are certain elements, certain semantic constructs, which in fact have substantial prior art that goes back as much as 10, 20, even 30 years in certain cases, that address the challenges that we're facing now, which is different from the way we addressed them over the previous 20 years. So in parentheses, it turns out, I'll represent the terminology used within the parallax execution model, but the general concepts are used by other models as well. The HPX runtime system developed at Louisiana State University is an example. Swarm, developed by ET International, is another example. Silk++ and TBB at Intel, Sandia's experimental Q-threads, some of the work out of Rice, surrounded by Habanero, and being incorporated in the new open community runtime, elements of Charm++, and I'm sure I'm forgetting something. My apologies to you if I didn't mention your favorite execution or runtime model. The use of lightweight user threads, no surprise. We appreciate the fundamental work done decades ago by Burton Smith that ultimately were implemented in the Cray MTA or XMT. Somebody correct me if I'm wrong. The use of these lightweight threads to reduce reduce overhead and to avoid blocking of the hardware is critical. In parallax, these are known as computation complexes because threads are fairly narrow in perspective. Driving those thread creations over long distance and helping to manage the system asynchrony while dramatically reducing the latencies, effective latencies in one hand, hiding latencies in other hand, is the use of message-driven computing. In parallax, we call these messages parcels. Berkeley calls them active messages. I think Jack Dennis and others called them tokens in the data flow days. I don't remember what Bill Dally called it on the J machine, and so on. Synchronization has proven to be a constraint, a bottleneck to much of computing. The use of global barriers and the BSP strategy has a number of deleterious effects, which I won't delineate here. The removal of such global barriers using lightweight synchronization but with very rich semantics can allow the computing to adapt to its availability and resources and adapt to the rate of computing on the part of the abstraction of the processing itself. This self-adapting allows us to take best advantage of the resources and respond to the ordered doing this computation in the global address space, which is something that we have avoided largely over the last 20 years, and for good reason, with which we toyed under the term PGAS, or Partition Global Address Space, with some success, implemented as early by Steve Scott, then at, was it CRI then? I've forgotten, or was it SGI? I don't recall, but in any case, with the T3E, and captured by my friend Bill Carlson's language UPC, along with others like Kathy Yellick. Touch on this, but we need something more powerful. We need something where virtual objects can move in physical space without changing the virtual names. That's not possible with those techniques that I've just mentioned. Adding to that in-memory checkpointing, we call that micro-checkpointing in parallax, and also being able to do heterogeneous scheduling, and we call that percolation in parallax. We find that there's a general consensus that these techniques are likely to address the challenges that Exascale is having. And so research in this area will become important. And I've already alluded to the other topics. The issue of data movement, most of the energy is consumed in data movement, most of the time is consumed in data movement. And so these characteristics, these elements which contribute to data movement become an important focus point. We've already talked about energy, and we've talked about programming models. The, again, emergence of domain-specific languages and declarative languages, declarative not in the pure sense, but in a hybrid case where the declarative constructs at least have to relate to the synchronization and scheduling, defining the constraint-based task instantiation, allowing the system to determine when that's going to happen. Well, if we're going to program these machines, we better have these machines. If that's the case, then I guess we're going to have to develop them and we're going to have to deploy them. Your guess is probably better than mine, but a good choice if we were given the charter, the goal, the resources, and the funding, as well as the cooperation of industry, government, and academia. That's key. It'll probably take about 5 years. Looking back at the HPCS program, which, let's see, how many machines, that's delivered how many machines? Oh, none. Okay. Sorry?
Almost one.
Almost one, thank you, Michael. Yes, almost one machine. Blue Water's near miss. That shouldn't irk anybody. The software, we're already too late for. Okay. I failed. The good news is if I'd gotten it right, there'd be more slides and we'd get out late. The bad news is I've only been able to establish a skeleton. But even doing so, there are a couple of things that we can see about this timeline. It really breaks down into two parts. The latter part, the latter 5 years, are really the design, development, and validation with deployment. We just can't speed that up very much. Yes, if we were in a war and, oh, we're in a war. Okay. Well, if we were in another war, then maybe we could speed it up. But taking care of IEDs and pickup trucks, that just doesn't seem to require exascale computing, or maybe it does. And so we have to expect that the timeline has to be, all of the research, all of the conceptual and advanced thinking has to be done before then. Well, we're in 2012, and let's look at this. So our biggest problem, I believe our biggest problem is we have yet to adapt an execution model that we can agree to, that we have tested and believe in, so that we can then co-design the hardware and software system around that, and we can validate that execution model with appropriate applications. We have not adapted that, but we are conducting today, under federal funding, experiments, initial experiments looking at the particular model, and that's the parallax model, or other models such as Swarm, such as Cyclops, such as Silk, which have many of those elements. So this work is beginning to move forward. A couple of months ago, the Department of Energy Office of Science, OSCAR, released the BAA for the XStack program. The proposals have been submitted. Rumors have it that numbers for 3 or 4 awards is, am I running out of time, John?
I just want to be closer to you.
What was that? I'm 1 minute over. We're almost done. The XStack program is an ambitious program that requires the development and interrelationship of execution model, runtime system, programming models, and other things that the proposers may feel are important. Notice I failed to say operating system. To develop a prototype in 3 years' time frame of a system that will both be of some value immediately and of long-term value leading to the exascale environment. That program is under review right now. That is to say the proposals are, and we are waiting for the results, anticipate the results sometime in May. I cannot understate the importance of this program. It will be particularly important and valuable to this country if I win. It's personal opinion. By 2013, assuming we've done that and we've taken a certain path, we should be able to start to formulate the architectures and benefiting from the Department of Energy's currently operating co-design program, which I think there are 3 of them, are based on applications and looking at communications, memory, access, and so forth. This will give us hard information that will drive our understanding of the requirements of exascale. And working based on an execution model to derive at least a base level programming model and an exemplar set of syntax from which we can develop simple translators and therefore do the runs. Understand we are already, without that interface, proceeding there. By 2014, we should be shaking the whole conceptual system out using simulation and emulation against real applications with the whole vertical integration, at least of the core elements of all of these pieces. It's assumed that by 2015, those who have large computer centers, like our friend Rupak out at NASA Ames, you will have your 100 petaflops machine there. We don't know what it will look like, but we know in his case it will be built by SGI. I wasn't supposed to say that. I'm sorry. We also know that at that time, the prototype software system, of which there should be more than one, and therefore we can compare and contrast, which should be delivered in the Department of Energy's XStack program. That brings us, at that point, to the design and development time that I mentioned before. This is a tight schedule, and it assumes that we are of a single mind and a single will as a nation and as a community to go forward with this. Any additional delays in this expectation will frankly break the schedule. And yet, if we step back, there are some fundamental questions that we don't ask ourselves, and that it's important if we're going to anticipate investing hundreds of millions, even $1 billion in hardware and software, or refactoring other software, for which there truly are billions of dollars of investment. You know, all of our basis for hitting an exaflops by 2020 comes from a silly graph from Jack Dungara, okay? And I mean no disrespect to Jack. And Hans Maurer, and Horst Simon, and Eric Strohmeyer, right? I mean, we understand science. In science, on semi-log paper, everything's a straight line, right? That was what I was taught when I was an undergraduate. These orders of magnitude just keep going by, and yes, you hit 2019 if you draw that. But is LINPACK, is the HPL benchmark actually the right measure for us to be doing this? And are we assuming that we're in the same part of the S-curve? Well, we're not. I should put up the classic graph that Burton Smith gave me with all the anvils coming out off the top. And if that's the case, is 2020 the right deadline? I hear colleagues, I won't mention their names or the big semiconductor companies they come from, but they tell me, we've got to work. We need the software now. But we don't know what we're doing. Well, then we have to do something anyway. This troubles me. All right? Maybe we need to know what we're doing before we go off and build something so that maybe it'd be the right thing. We're also assuming that complexity of operation is, in fact, has to be a product of complexity of design. I always hear it's going to be harder to program the Exascale machine than today's petaflops machine. It's going to be harder to design them. I disagree with both of those things. I believe we're looking for a different abstraction of emergent behavior from machines based on highly replicated, rather simple devices. Hardly a new idea. It was first implemented about 4 billion years ago. I think it's called life. And then the whole question of what is it we're actually processing? There is an understanding that there's a tremendous new class of problems. You know it best in search engines and social networks called graph processing. And that, in fact, is becoming an ever larger part of the number of cycles. So why should we be building a Fortran engine for the next generation that's going to be running graphs? We should be building graph engines. So, and yes, conclusions mean last slide. In conclusion, we don't know how to build an exascale machine. We don't know how to program it. We don't know what the execution model is. This is different from previous goals. We knew how to build a terascale machine. We knew how to build a petascale machine. Didn't mean it didn't take a lot of work, and the technology had to get there, but it was the same paradigm. We don't even know how to organize such an effort. But fortunately, under leadership of the Department of Energy, we're beginning to see some hope. We're beginning to see some formulation of a path forward, though it's still in its inchoate phase to do this. It must be understood, I'm sorry, I hate to tell the vendors this, but we have to do the research. We don't know, so we have to find out. And the development we have to expect takes time. We can't assume it'll just be done in 2 to 3 years after we come to the answer. So, my final comment. Is 2020 too optimistic? If we force ourselves to meet a 2020 timeline, will we want what we end up in 2020? And what, in fact, is it that we want? Thank you very much.